Okay, this is chapter 14, lesson 2. In the previous lesson, we derived rate laws from experimental data. So we had tables, and we analyzed the initial conditions or initial reaction rates based on the concentration, and we were able to get the rate law of the reaction. We're going to, in this lesson, do the same thing, but we're going to get the rate law from graphs, from graphing the reaction as it proceeds. So this is a different method. It gives you the same thing. It still gets you the rate law, but from a different angle or through a different way. And we know that graphs really are just representations of equations. So equations and graphs are essentially connected. So we're able to get the rate law and the constant also, k, from the graphs. If some of this doesn't make exact sense, some of this, the mathematics behind this is a little bit complex, don't worry too much. Just think about remembering how these flow. So what we've got is we've got a reaction, very simple reaction. One substance becomes another. So you can say A turns into B. And we collect the data as the reaction runs, and we decide to graph it. So in this case, a curve is produced. That looks like this. We've seen similar curves before. We see that the reaction is higher at the beginning, the reaction is lower at the end, meaning the rate is higher because the slope is more steep. The rate is lower toward the end, the slope is less steep. So this is simply, this is reaction just running a set of conditions all the way through to the end. This is, say, starting with a concentration of reactant and just watching it as it goes. Now, the way we're going to get the rate laws is, here it says, if you take a look, we can determine that the concentration does have an effect on the rate. It does have an effect on the rate. And the reason it does, and the reason we know it does, is because the slope changes throughout. We know that as the reaction proceeds, the concentration decreases. So reaction progress, the reactants are constantly being used up, so you have less and less and less reactants as time goes on. And because the slope of the line changes throughout, so you begin with a steep slope, you can say, and then the slope decreases. Eventually the slope will flatten out. And because the slope changes, remember, slope gives you the rate at which the reaction, the rate of the reaction throughout the reaction. So because the slope changes, the rate changes, which means the concentration affects the rate. This is the whole point. Concentration does affect the rate. So our rate law will have some sort of order. That's the idea. But what kind of order is the question. So what we'll do to help us determine the order, what we'll do is we'll have to somehow manipulate the graph so that we get a straight line. What we're going to do is we're going to manipulate the graph in all these cases until we get ourselves a straight line, because a straight line is a line that has a slope, and this slope will give us our constant. We'll be able to get a constant. A constant doesn't change, and so we have to get a slope, a straight line. We have to make the graph into a straight line, and there's a number of ways of doing this. Mathematically, what we'll first do is we'll take the natural log. On your calculator there should be an ln button. So if you take the natural log of each one of your reactant concentrations, of each one of these numbers, and then you graph that, well, let's see what we get. You actually get a straight line. So these are the natural logs of the different pressures. Again, don't worry too much about why this is done, but when our pressures, when our concentrations, in this case it's pressure, when the pressure is plotted against time, when the natural log of the pressure is plotted against time, we get a straight line. And when we get a straight line, then we know we've arrived at the rate law. And we know that our constant can then be essentially calculated. And if you get a straight line from the natural log of your concentration or your pressure, then this will be a first order. This is really a matter of remembering it. If you directly, by taking the natural log, you get a straight line, this is going to be a first order process. So, and then we can determine the slope of the line. Remember, the slope is rise over run, and by taking rise over run, in this case, we can take 2 points on the curve and do rise over run. Say we can take these 2 points, and we roughly, if we analyze this, we should get, when you do rise over run, we should determine that the slope is this number. Now here it says we have to take the negative of the slope. Because this slope is negative, the rise, you can say, is negative, the run is positive, you'll get yourself a negative number, so just remove that negative, so that way you get a positive k. K's will never be negative, k's will always be positive. And so, in other words, we can first determine the order by plotting the natural log, and then we can determine the constant by calculating the slope from the graph. For a second order process, like the one here, what we'll take is, for this reaction, we've done the same exact thing. We first plotted it, and it did not give us a straight line. We then decided to take the natural log of the concentration, like we did in the previous case, and it still did not give us a straight line. Notice a straight line would look more like this. So, if the natural log does not give you a straight line, the reaction is not first order, and there is one more step that we can take. We can try to get a straight line by taking the inverse of each one of these concentrations. So on the next slide, so here it says the plot is not a straight line, so it is not first order. If the natural log were to give you a straight line, it would be first order. But what we'll do here is we're going to graph the inverse of the concentration, which means we take each concentration and do 1 over that, and then we plot it, and notice we have a nice straight line. If we have a straight line, this means we're ready to take our constant. Our k, which is a constant, doesn't change, corresponds to a straight line, so we're ready to work with it. If the inverse of the concentration gives you a straight line, it is a second order reaction, or a second order, it is second order in that reactant. And the slope in this case is simply your constant. Again, if you take rise over run, you'll be able to get yourself your constant. Again, you can just take 2 points here and determine the constant from this process. And then finally, we could ask, well, what if I have a zero order process? What if one of the reactants in my reaction is zero order? What would that look like? Well, a zero order is the simplest, even though we're talking about it here last. What you'll do, whoops, there should be a graph here, probably not. In this case, a zero order will actually give you a straight line to begin with. So if you have a zero order reactant, you'll get a straight line, which means the concentration does not affect the rate. So here if you have time, and so you have concentration here, throughout the reaction from the beginning to end, the slope stays the same, which means the rate isn't changing, which means as the concentration of the reactant goes down, it does not affect the rate. So again, this would be like the reactant is zero order, and that's the idea here. And this it says the same thing here in the description. So that would be a first order process. So real quick to summarize, a first order process gives you a straight line when you take the natural log of your concentration. A second order process gives you a straight line when you take the inverse of that concentration. And a zeroth order, I guess you can say, you get a straight line to begin with, meaning just by graphing the concentration you get a straight line. So this gives you the individual order of each. So if you had a reaction that involves, say, 2 or 3 reactants, what you can do is you can check how each one of them affects the reaction, and then you can write the overall reaction. You can still say, well, the rate, therefore, you can say is A is to the second order, for example, and then we can put the constant in there. And the constant then will be determined from the straight line. You'll do rise over run to get the slope of the constant, and that's how you would determine the rate law for a reaction like this. Okay, and this should conclude for us lesson 2 of chapter 14.